Hello everybody, my name is Alejandro, PhD student working with the Software Analytics Research Team from Universidad Italiana in Switzerland and with the Software Design Lab from Universidad de los Andes in Colombia. And I will be presenting our research article entitled Investigating Types and Survivability of Performance Bugs in Mobile Apps, which has been published in the Empirical Software Engineering Journal. This is a collaboration between la Universidad Italiana, la Universidad de los Andes, and the Gran Sasso Science Institute. Our research takes place within the mobile devices environment, to be more specific, mobile apps, which nowadays represent a major percentage of our whole usage when we are employing our phones. Therefore, as users, our experience strongly depends on the quality of the apps that we use, and code quality can actually have an impact on the success of mobile apps. When we talk about quality, we do not simply refer to the features offered by the apps, but also we are talking about its non-functional characteristics such as security or reliability, and especially in the context of our work, performance. Performance bugs have been studied for several decades by researchers and practitioners. They can hurt the satisfaction of end users, and if performance targets are not met, they can cause delays, failures on deployments, redesigns, or even a new implementation of a system, and worse, total abandonment of our projects. This might be eventually perceived as lost income or business failures. Then, in such scenario, it's important to understand the impact of performance bugs on several aspects in our projects. This is essential in order to improve the quality of the software, and that is how the goal of this study is to broaden knowledge about performance bugs occurring in native mobile apps. And when we say native mobile apps, we refer to both of the most popular operating systems, Android and iOS. We address our goal by answering two research questions. We explore the types of performance bugs affecting mobile apps, and we investigate how long it takes to fix performance bugs in mobile apps. So let's talk about the study context, namely the data used in order to answer the research questions. First, as a baseline, we have 100 apps per platform hosted on GitHub. Second, we extracted the change history with a crawler. Third, we identified commits in which the developers are fixing performance bugs. And finally, as a result, we obtained 1,396 candidates commits coming from 78 different apps. We cannot claim that this set of apps is representative of the whole population of apps. However, the heterogeneity of the considered apps may foster the generalization of our findings. Having this context, we can proceed with the first research question. Which types of performance bugs affect mobile apps? Considering our main context, we manually analyzed the candidate commits. Around 1,000 commits were manually tagged by the authors, and we ended up with 500 bug-fixing commits concerning performance aspects, 250 for each platform, plus 510 commits which were classified as false positives. These tags were used in the definition and creation of a taxonomy for each operating system. And concerning Android, the performance bugs most frequently affecting this operating system are related to resource leak, having 96 instances. This category groups all the bugs that are related to improper handling device resources, mostly because of bad programming practices. Within this category, the most frequent category is memory leak, a scenario in which the app incorrectly manages memory allocations. As an example, let's inspect this snippet of code. This snippet of code is in charge of loading the photo of a given contact and uses a cursor to access the result retrieved from the database. Then one must implement the close method in order to release all resources, but in the buggy version, the cursor object was not closed after its usage, leading to a memory leak. The problem has been solved by invoking the close method on the cursor in the finally block. In addition to the categorization, we also identify how the bug types can potentially and negatively impact performance factors. We extracted a list of performance indicators, and for each bug type, we define its impact on every performance factor. This table is showing only the macro categories, but the procedure was done for every single subcategory. Takeaway concerning this evaluation: resource utilization is the most affected indicator. Now, in relation to iOS, the performance bugs most widely diffused are related to resource leak, same as Android. And within this category, the most frequent category is memory leak, again, same as Android. As an example, this snippet shows a case of unreleased objects bug fixed in the Little Go iOS app, again for this platform. The fixing of the bug consists of the addition of the auto-release keyword in the return statement, and this allows the developer to ask the allocation of the return object from the memory, but not immediately. With iOS, we also identify the impacted factors, same procedure, definition of the list of factors, and for each category and subcategory, an impact was defined. Once again, we were able to highlight that the resource utilization factor is the most impacted factor. Having defined performance bugs that one can find within native mobile apps, we proceeded to our second research question. How long does it take to fix performance bugs in mobile apps? For such purpose, and as a starting point, from our study context, we take again our 500 commits related to fixing performance bugs. Within the change history, we already know the date in which the bugs were fixed, and now we need to know when those bugs were introduced. Using the SIGSOFT algorithm, we were able to identify at least one bug-inducing commit for 380 commits. And then we assessed the survivability in days of performance bugs. Since more than one commit can be indicated by the SIGSOFT algorithm as responsible for inducing the performance bug fix, minimum and maximum estimations of survivability were presented. Then we identify the survivability intervals when, first, considering all the analyzed performance bugs together. Second, when grouping them by mobile platform, namely Android and iOS. And to ease the interpretation, we also identify the survivability intervals when considering bugs unrelated to performance issues for Android and iOS. Interesting results to highlight. First, the long survivability of all the analyzed performance bugs. The number of days needed to fix an introduced performance bug is on average 98 days, and it grows to 342 days for the maximum estimated survivability, which is higher as compared to that of bugs unrelated to performance issues. And second, performance bugs have a similar survivability in Android and iOS apps. And that is how we addressed the second research question. In conclusion, as key takeaways and contributions, first, we defined a detailed taxonomy of performance bugs affecting mobile apps. And second, we found that performance-related bugs tend to survive longer in the apps. Before finishing the presentation and as a wrap-up, I will summarize our journey. I present the context of our study and the motivation, followed by the importance of this research and our main goal, which was addressed by two research questions. I explain how we extract the data used in the research, data that allow us to first define a taxonomy and a list of impacted factors for each platform, and second, to check the survivability of the performance bugs in the systems. Concluding then with our key contributions and takeaways. Thanks for watching.